Okay, so the table here is going to help us look into something called the general addition rule, which is a means of calculating probabilities of A or B in situations like this, basically compound events. So we'll start with problem number 28. It says, pharmaceutical company is interested in the opinion of the elderly because they are receiving either Medicare or will receive it soon. What is the probability that the selected subject is someone 60 and over who responded? So we'll start out with that just to kind of get familiar with the data set. I'll write that as probability of 60 plus who responded. So probability of somebody who's 60 plus and responded, that kind of limits your data set. We're no longer talking about the entire data set. We're talking about just a little piece of it. We're talking about the piece right here. So we can kind of block out everything else. What's the probability that they responded out of the 251 people that are in that group? Well, how many people responded? 202. 202 out of the 251 people. So a little bit above 80%. Now, I guess there's another way you can look at this. What's the probability of randomly selecting somebody in this group who responded? You could also, and I guess another reading of this would be 202 out of the 1,205 people in the survey. So that's the number in this survey who responded. So I guess I took a little different look at it first, that we were just looking in this group to see the probability of people who responded. I'll try and make sure that for the test questions that I give you that I'm pretty clear which one I want. This one or this one. But what we're more interested in is working with something called the general addition rule. And we can see that with problems like number 30. So problem number 30 asks us to find the probability that a selected person refused to respond or is over 59 years of age. So let's let R represent the event that the person refused, and we'll do 59 plus to be the event that the person is over 59 years old. So a person is basically 60 and up. So person is in the 60 plus category. So let's understand then what we're asked to find. We're asked to find the probability of R or 59 plus. Probability that they either refused or they're in the 60 and over category. So let's look at those two computations, or those two groups. The probability that they refused would be all these people. So there's 156 people that refused. So we can do the probability of refusal is 156 over 1205. Let's calculate the probability that somebody's in the 60 plus category. In the 60 plus category, we had all these people. So there was 251 people in the 60 plus category. So plus 59 plus So it'd be 251 people out of 1205. Now I've done this in color on purpose. Do you see that there's a little bit of a problem with our calculation as far as trying to find, one category or another? Where's the difficulty? Yeah, it's where they overlap. This little segment got double counted. So you gotta subtract off that segment. And the way to describe that segment is where they intersect. Probability of R and 59 plus. So that'd be 49 over 1205. So that gives me a total of 358 over 1205. The author seems to like rounding off these probabilities to 3 decimal places, so I'll follow suit. 0.297. But the key thing here is that we're using what's called the general addition rule. And that is when you subtract these things, you got to subtract that double counting. So the general addition rule. Probability of A or B is a probability of A plus a probability of B minus that little piece of double counting, P of A and B. Now there's a special addition rule. Special addition rule. And that's when A and B are disjoint. The other word for disjoint is mutually exclusive. One excludes the other. Now the thing about mutually exclusive events or disjoint events is that they can't occur at the same time. A and B just don't happen at the same time. So this probability is just 0. You don't have to worry about it. And in that case, you can calculate probability of A or B just like you might like, which would just be adding up the probabilities. Because that part is 0. There's no double counting when your events are disjoint. Okay, let's back up a step and try a different one. Problem number 22. We'll do 22 and then 24. Before I move on to those, are we okay with problem number 28? Good on that one? This is the kind of stuff that I'd want you to be able to calculate for an exam. So make sure that you're comfortable with this. And like I said, we're going to do some more examples. Okay, so one thing I like about the author is that he pulls in a ton of real data. He must spend a lot of time collecting all of this stuff. And so let me copy down another table for us here. And it's correct dosage calculation and wrong dosage calculation. So that's across the top, and then down the side are different labels, and want to see what happens to doctors when they're presented with different labels. Concentration label, and then ratio label. So the data set here is the number of correct and wrong dosage amounts calculated by physicians in research experiment, one group of physicians was given bottles of epinephrine labeled with concentrations of 1 milligram in 1 millimeter solution. Another group was given bottles labeled with a ratio of 1 millimeter in 1 millimeter of a 1 to 1,000 solution. Two labels describe the exact same amount. The physicians were instructed to administer a 12 milligram or a 0.12 milligram dose of epinephrine. So basically, how good are your physicians at a little bit of a basic math? Well, with the concentration label, 11 people got it right and 3 got it wrong. With the ratio label, 2 got it right and 12 got it wrong. So I think I know what label I want on my doctor's medicine bottles. But maybe that's up to the pharmacist, not sure. Let's see, there's 14 here, 14 here, and 28 here, 13 and 15. Let's answer a few questions based on this data set. Problem number 22 is what we'll start out with. If one of the physicians is randomly selected, what is the probability of getting one who calculated the dose incorrectly? So let's let WD represent the wrong dosage. Probability of WD will be what? Yeah, 15 over 28. More than half the doctors in the study. That's not reassuring. 15 over 28. A little frowny face on that one for sure. Yeah, there's 15 wrong doses out of 28 people in this little study. But let's move to the part of the problem that I want to discuss the most, which is problem number 24. I let WD represent the wrong dosage. Let's let R represent the event that somebody selected at random is somebody who got the ratio label. Ratio label. So what problem number 24 essentially asks you is, if one of the physicians is randomly selected, find the probability of getting one who made a wrong dosage calculation or was given a bottle labeled with a ratio label. So basically, it turns into probability of WD or R. So again, let's take a look at these things. Probability of WD, the wrong dosage, that's this column right here. These are the people who got the wrong dosage. And R is our ratio label. These are the people who got the ratio label. So again, you can see that there's a little bit of a double counting. What I want you to do is fill in these probabilities. It's probability of WD plus probability of R minus probability of WD and R. So see if you can't fill in those probabilities. And let me slide it down a little bit so you can see the table. I'm going to kind of walk around and see how you're doing, help out a little bit. If there's some questions, please let me know. If you're watching this at home, you can fast forward until I remove that little paused sticker. Okay, so a quick sample, certainly not a census, but a quick sample. Looks like a lot of you are doing okay on this one. So probability of WD. Well, probability of the wrong dosage was from the first part, that's 15 over 28. Had that from the up above. What's the probability of getting a ratio label? Good, 14 over 28. And their intersection, where do they overlap? How many people had the wrong dosage and a ratio label? 12. 12 over 28 for a difference of 17 over 28. Yay. Okay. Let's do one more like this, and then we'll move on to the complementation rule a little bit. Yeah, question? You know, I'm most happy with fractions, generally speaking. So, and if there's something that I wanted in particular, if I wanted you to calculate a decimal value and then round to a specific place, then I'll mention that specifically. But I'm probably happiest having a fraction there. Yeah, thanks. Like I said, let's do one last one like this. And it's going to go back to, I think, the table that's given at the front of this section. So problems 33 through 35 go all the way back to table 4.1, which is at the beginning of this chapter. So it's this table on the intro page of this chapter. And I'll copy down the table for us right here. But if you want to pause the video or something like that and check that out, there you go. One last look. So we had people who were being tested for drugs with this test, and you had those who had a positive test result. Test result. And there were also people with a negative test result. And then there was subjects that used drugs and some that didn't. Not being judgmental here. So, subject uses drugs. Subject doesn't use drugs. So we had 24 people here, 3 here, and then 119, 154, So that gives us a total of 300 people in this study. So marginal totals of 143, 157, 300, 122, and 178. Let's table 4-1. Oh, you know what? I'm sorry. You're right. It's not that table. But it is described in the problem, I think. I thought it was table 4-1. My bad. All right. You know what? I did have in my notes these numbers you kind of have to calculate, because what they do is they give you enough information to calculate these. You might want to make sure that this table is copied into your notes, because as you do problems in the book for your homework, let's see, starting with 33, 35, and 37, you'll want this table. So we've got it for ourselves here. And we're going to look at several probabilities. So, you know what? I was wrong. It's not table 4-1, which is like kind of a bummer for me, but I'll live with it. It is described here. So if you look at the description, you kind of have to come up with these numbers on your own to an extent. So they tell you that 144 subjects with false positive tests and 24 with false, let's see, 143 subjects with positive test results. There are 24 false positives, 157 negative results. There are 3 false negative results. 150 negative results, 3 false negative results. So they're telling you some of the marginal totals. They told you that there was 157 negative results, and there was 150 negative results, 3 false negatives. 143 positive results, and 24 false positives. So basically the subject didn't use drugs, and yet they tested positive. Okay, I'm not sure I said that last one right. 143 positive results of 24 false positives. Let's look at problem number 34. And I'm going to define 2 events. Let's let plus the event that the person tested positive, and M. Now this is a little bit of a disconnect for the problem, I think, because the problem talks about drug use, but the table talks about marijuana use, which, okay, marijuana, if you want to call it a drug, that's fine. But I don't know, it seems like the should be a little bit more in accordance with what the problem says. In any case, M is the event that the person uses marijuana. Person uses marijuana. And we'll just lump that into the larger category of drugs. So the question is, what's the probability of a positive result or the person uses marijuana? So P, a plus, positive result, or M. addition rule on this one. Okay, so using our general addition rule, it's going to be the probability of a positive result plus probability of m minus the probability of the intersection of these two. So the probability of a positive result is going to be 143 over 300. You had 143 positive results out of the 300 people surveyed. Probability that they use marijuana was 122 people out of the 300 minus their intersection. Probability of their intersection, there's 119 people who had a positive test result and used marijuana, 119. So over 300. Basically, you're just adding those extra 3 people in. 146 over 300. I don't even care that this is not in lowest terms. I'm just happy to see the probability. Some of you calculated percent. That's great too. Okay. Are you feeling comfortable with the addition rule? That's the easy one to get. In the next section, we're going to work on the multiplication rule. That's going to be a little bit more challenging and thoughtful. For now, let me finish up with the complementation rule. So, complements. There's a nice Venn diagram on page 152 that kind of shows what's going on with this. So this blue box represents what's called your sample space. And you've got 2 different events. You've got A and A bar. A and A bar are kind of like heads and tails, or rolling a 3 or not rolling a 3. They're complementary events. It's one or the other. So in this case, here's event A, it's everything in yellow. Here's event B, it's everything in blue. So you're one or the other. Can you be both at the same time? No. Sorry, Spartan fans, there's no green here. All right. But it's one or the other. Now, what that means for us is if you're looking at the probabilities, the probability of A plus the probability of not A is 1, or the complement of A. That's everything that can happen. You're either in here or you're in here. Because we have this probability kind of equation, it's A or not A, then we can get a couple more. So let's keep track of a few things. Probability of A plus probability of not A equals 1. We're going to take advantage of this in the next section, or actually maybe 2 sections up. I can move this the other side, get probability of A equals 1 minus probability of not A, or vice versa. Probability of not A is 1 minus probability of A. This is a nice example we'll do talking about birthdays in a little bit. Now, this might sound a little bit theoretical and a little bit strange, so let's kind of bring it down to earth with a nice friendly example. Problem number 14. It says, according to the National Association for College Admissions and USA Today, 19.8% of college students take at least one class online. What is the probability of randomly selecting a college student who does not take any college classes online? So, see, the probability of finding somebody that takes an online class, at least one, is 19.8%. Let's call that 0.198. What they're asking you for is the complement of this, probability that they're not online. How would I find that probability? 100%
minus 19.8%.
Yeah, thank you. So the 100% or our 1 minus the 0.198. Do you think it's likely that you would randomly select somebody taking college classes that's not taking any online classes? Yeah, it's probably more likely than not, right? 80% chance. Let's try another one to kind of follow up on that one. Problem number 16. And this time you're going to have to do some thinking on this one. Got to hand it to the author. He works hard to get some data. It says, when the author observed a sobriety checkpoint conducted by the Dutchess County Sheriff Department, he saw that 676 drivers were screened and 6 were arrested for driving while intoxicated. Based on the results, we can estimate that P of I is 0.00888, where I denotes the event of screening a driver and getting someone who is intoxicated. What does P of I denote, and what is its value? Oops. Wake up. There. All right, so that's your question. First of all, describe what P of I bar represents, and then secondly, describe its or calculate its value. Okay, so what does P of I bar? What's that probability reflect?
Those that are not intoxicated.
Yeah, probability of finding somebody that's not intoxicated. So the probability of finding someone who is not intoxicated. What is that probability?
670.
Oh, nice. Nice. I was just looking for this. 1 minus 0.00888. 0.99112. But yeah, if you did it the other way, that's fine. So you can take that. I don't know. Excuse me. 0.99112 times 676. Is that how many people were in the study? Yeah, so about 670. Yeah, so that reflects what the author was saying, is that 6 were intoxicated, meaning the rest weren't. So good. Either way, for homework in this section, section 4.3. Try problems 1 through 25. Do them again. I'm kidding. Yeah. 1 through 25, 33 through 37. As always, those are just the odds. All right. Good luck on those.